Another application of an operation amplifier is an integrator. An integrator is a circuit that will perform the mathematical operation called integration. So, integration is a process of continuous addition. The most popular application of an integrator is to produce a ramp of output voltage, which is linearly increasing or a decreasing voltage. So, when you are applying a step voltage, the output, it is a continuous addition, so the output normally will be a ramp function. See, this is a step function like this. Output will be a ramp function continuously increasing or decreasing. So, the circuit in which the output voltage is the integral of input voltage, that is the integrator circuit. See the circuit diagram of op-amp as an integrator. Already you have studied an inverting amplifier. It's quite look like an inverting amplifier. The difference here is, instead of your feedback resistance from output to input, you have a capacitor. There it was a feedback resistance called as RF. So now here it is changed to a capacitor. And the way how you are deriving your output voltage, the same manner as we have done for an inverting amplifier. Equation, only thing in this loop we have to consider the voltage current equation of a capacitor. So I will show you now how to get the output voltage for a integrator, how to derive the output voltage for an integrator circuit. So now here you can see the current flowing through this, assume as a I1, and current through this capacitor assume as a IF. See, positive terminal of this integrator is grounded, so it is in inverting configuration. So now we are deriving the output expression for an ideal integrator circuit. So this is an ideal integrator. See here, the voltage of non-inverting, it is grounded, so voltage at this point is equal to 0. The voltage at this point is equal to 0. It indicates that the voltage at this point also should be equal to 0. So what is the current in this branch? The current in this branch, that is written as I1. I1 is equal to V1 divided by R. Now, what is the current in this branch? See, it is a capacitor, so you cannot apply the resistance equation over there. You know the capacitor equations. For the capacitor, I is equal to C dV by dt. Keep it in mind, this is the voltage current relations for a capacitor. I is equal to C dV by dt. That means if a change in voltage is there, capacitor has current. If there is DC voltage, that means dV by dt will be equal to 0. In that case, current I will be 0. So for a DC voltage, the current through the capacitor IC will be equal to 0. So capacitor will be open. For a DC voltage, capacitor will be open circuit. For an AC voltage, capacitor will work. Now, so the current I can write through this capacitor, that is IF. IF I can write from this relation as IF is equal to C, the voltage, this will be the output voltage, V out minus V0. So C dV dVO divided by dt. That is the output voltage. That is the current IF. Now, what is the total current here? If I am applying KCL at this junction, I1 is entering, IF is entering, and no current can flow to the negative terminal of an op-amp. So, this branch current is 0. So, two currents, IF coming to the junction, I1, and IF also coming to the junction. So, we can write it as, on KCL on junction, we can write it as I1 plus IF should be equal to 0, or which implies that I1 should be equal to minus IF. Now substitute the value of I1 from here and IF from this here. So what you will get as V1 divided by R, that is I1, should be equal to IF is minus IF is C dVO divided by dt. So V1 is the input voltage. I can write it as V1 should be equal to minus RC dVO divided by dt. Now from here I can write dVO as, dVO should be equal to V1 into dt divided by minus RC. Now, for getting the V out, I have to take the integration on both sides. So, integration dVO should be equal to minus integration V1 dt divided by RC. See, integration of dVO will be VO, should be equal to minus RC is a constant for integration. So, it can come out of the integration. It is 1 by RC into integration V1 dt plus you will be having an initial voltage V0 something, integration constant is there, it will be normally equal to 0 you can consider. So, you can see that your equation will be V out is equal to minus 1 by RC. It is a constant and integral of V1 dt. So, integration of your V1 is input signal will be your output signal. So, that is the reason we are telling that this will be doing an operation of integration. So, finally, I will write by equation V out should be equal to minus 1 by RC integral V1 dt. And if under the condition I am taking the no initial voltage at the output. So, this will be the equation for integrator, an ideal integrator. So, the problem over here is if the input voltage we are applying is having a low frequency. Low frequency input voltage, what is the action of a capacitor? For a DC voltage, capacitor is open circuit. So, of course, open circuit means it will offer a very high impedance. So, low voltage, low frequency comes here, the capacitor impedance will be very high. So, this impedance is too high, that means the gain of the circuit, the impedance over the feedback path divided by the input resistance. If this factor is so high, that means gain of the circuit is very high. So, in ideal integrator case, initial frequencies, that means low frequency of the input, we will be getting a very high amount of gain. So, for that may not be possible when you are doing practically. So it's not because so low in frequency you will get a very high output because of this high gain. Should not happen. So for limiting the gain at the low frequency, we will be putting a resistor parallel to this integrator, ideal integrator. Then it becomes the practical integrator. So for the practical integrator parallel to this capacitor, I will be having an extra resistor like this. This is a RF. So this is the circuit of a practical integrator. This one is the same circuit we are going to do in the lab. Now see here, already I told you, low frequency case you will be getting a very high gain, so the output will be very high than it is not measurable. So in that case, if you have a resistance parallel to this, you will be able to limit the gain of the circuit. So that is the reason we are putting a resistor parallel to this capacitor for limiting the high gain at low frequency. For limiting the high gain at low frequency. So here, suppose if I am taking the condition gain is equal to 1. Gain is 1. Indicate that V out should be equal to V input. V out by V input is equal to 1 or V out is equal to your V input. In that particular case, the corresponding frequency gain is equal to 1 means I can write the gain in dB should be equal to 0. So if I am plotting the graph of frequency versus gain, I am going to plot in dB range frequency versus gain. So for an ideal integrator, it will be something coming down straightly like this. This is the case for a ideal integrator. And that means initially you will be having a very high gain. But comes to a practical integrator, the initial high gain you can limit by providing this resistor. So the initial high gain I can limit so that I have the response something like this. So this is for the practical integrator. So the initial high gain here we are limiting to, this is a straight line like that. When I have drawn it becomes somewhat twisted. So this is the practical integrator. So initial gain we have limited over here. So that means the point here, the frequency corresponds to this point. The gain is equal to 0. Gain in dB equal to 0. That means actual gain is 1. Output should be, actual gain is 1. Output should be equal to your input. In that particular case, I can define the frequency FB as per your equation when you are deriving, you will be getting it as 1 divided by 2 pi into RC. So if you are choosing this value of frequency, if it is 1 kilo or 2 kilo, you are designing where you want exactly your output should be equal to input, you can get the values of R and C. Then the gain of the circuit you can calculate your RF. So this is the design we are incorporating in your lab, and so that's about the practical integrator. Now comes to summing integrator. So already we have told you about summing amplifier. See, when I have drawn here an ideal integrator, it looks similar to a inverting amplifier. Only different, this resistance RF is replaced by a capacitor C here. Same way, after that we have studied the summing amplifier. And in the summing amplifier,